So just to start the paper off, I'd like to talk a bit about game flow and dynamic difficulty adjustment. So with game flow, the concept of game flow is the balancing of the player's skill level and the level of challenge in order to avoid feelings of frustration, feelings of boredom, to keep the player entertained, to keep them in that flow channel in order for the game to progress, I guess, smoothly and just to keep them happy throughout the game. And with dynamic difficulty adjustment, that's pretty much just adjusting the difficulty as you go rather than stopping the game and having to do it manually. And there are of course different methods that you can use to do this, such as reinforcement learning, dynamic scripting, probabilistic methods, of course a lot of other different methods that you can use. For games themselves, there are a lot of different approaches that you can take. And two main kind of areas that people tend to focus on is changing the environment and changing the obstacle itself. Now, to look at some examples, for example, in Left 4 Dead, for keeping game flow and for applying DDA, they actually have human player bots that help the player throughout the game. They provide support. They also have ways to change the enemies slightly if the player is struggling. Another game that provides DDA is actually Mario Kart. It has a rubber band AI, and it tends to help. It tends to help the player throughout the game. So if the player is very struggling a lot, they will actually boost the player up, and they'll feel like they have more of a chance. If the player is doing too good, they'll boost the other kind of bots or other players that are behind the actual player. Just looking at the aims of our project, it's mainly to focus on games that contain turn-based battle systems. It's to explore the use of reinforcement learning to achieve dynamic difficulty adjustment and game flow. It's specifically to target enemy obstacle, or the obstacle, rather than the environment. And we create a simple game to test these sort of ideas. And that is to show that this approach and method could be worth exploring more, and it can eventually be applied to more complex games in the future. So now, just looking at the game, this is a very simple game that we created ourselves, and this is just a screenshot from the game. And I'm just going to go through the elements of the game very quickly, just so you can have kind of an idea of it. So on the left is the actual player character, and below him is these numbers indicate the health points or how the player can live, and 72 indicates kind of the current health point, 75 is the max. The slider is just a visual representation of the health points. Below are the 4 different moves that the player can use, and the opponent itself, the agent, can use them themselves. And lastly is just the flee button, and this is just to end the game. So the mechanics, this is just a turn-based game. So that means that each entity gets a turn to pick a move. These moves are done one at a time. Damage calculations are performed and applied. And once someone hits 0 HP or 0 health points, that just signals the start of a new battle and everyone's returned to their initial state. So just a small demonstration of the different moves. So first is the move hit. And here you can see that just by pressing the button, the damage will be applied. And this is just a simple move, a very weak move that's pretty much just used as a control. Next is charge. This is a more stronger move that players would tend to prefer to use. Next is combo. It's also a stronger move, just applied in a slightly different way. And lastly is heal, and this just gives the player 10 health points back. So you see it can go from 64 back to 74. So now, looking at the reinforcement learning agent, and for the reinforcement learning agent, we decided to go with Sarza. For these type of works, people usually tend to go with Q-learning. And while Q-learning is great, it tends to focus on the max kind of output. Well, we're looking more to establish kind of a flow to the game. So we're not always looking for the best outcome, but rather what's kind of good for that moment, but might be better for, other moves might be better for other. So the states for the agent are based around the health points of both of the entities. They're divided into 3 groups. So if one reaches 0, if both of them are equal, if one is greater than the other, it also depends on the value of the HP, which just means that you want the agent to know exactly where it is at that point. If it's between 75 and 65, it knows it's kind of towards the start of the game. If it's kind of between 15 and 1, it knows it's kind of going towards the end of that battle. So next, just setting up parameters, and we're going to be looking at entities, the rewards, and the exploration and exploitation rates for the agent. So the entities are, of course, just the player and agent. The rewards, we tested 2 different sets of rewards. So a positive reward of 100 for the agent for winning, and a minus 100 kind of penalty for losing, and then positive 50 and negative 50 kind of for winning and losing. And we also established kind of a rule that if the agent tends to win more than 5 times in a row, we can see that the player is actually struggling. So in that case, we flip the reward and the penalty. So now the reward for winning will actually be negative, and the reward for losing will be positive, and it'll try to encourage the agent to lose rather than to win, so that the player can maybe feel a bit more at ease, can try to adapt a bit more. For the exploitation rates, we tested 3 different rates, and that's 30-70, 50-50, and 70-30. Just looking a bit at the evaluation. For study 1, we looked at agent development, and we had 4 different sets of participants, male and female, different ages, different levels of experience. In total, there was 10 games played, all with different settings, but with using the reinforcement learning agent. And each of these games had at least 30 battles. So things we observed would be like the agents and players, move usage, the patterns in the agents' games, and outcomes for each of the battles. So just looking at the most kind of used moves, if you look to the left, you can see that the agent really focused on using heal. So it'd be, that was something it favored a lot. Whereas the player would favor combo and charge, moves that are very strong, and that would kind of give them more of an advantage and to end battle quickly. So for the least used, the agent kind of favored more least favored hit and charge, while the player least favored hit and heal. So there's a bit of a difference with the players not really using heal as much, but both of them kind of recognized more or less early on that hit wasn't as useful, and it was kind of a weak move. The agent maybe needed a bit more time to completely realize that, but the players took a lot less time. So just a quick look at games A and B. For the agent game, they used both rewards of 100 and penalties of minus 100. A had an exploitation versus exploration rate of 50-50, while B had an exploration versus exploitation rate of 30-70. And A was kind of just more of a typical game. It showed, both following game A, you can see how most of the typical games went, with the agent using heal most often, followed by combo, kind of least using hit and charge, and kind of the patterns as well. They'd be repeated a lot throughout the other games. Whereas B tended to kind of avoid certain patterns that were present in the other games, and actually it didn't use heal quite as often, and that might be due to the rate of exploitation that was used for that agent. So now just looking at this graph, this is just a graph of how the HP went throughout time. So at the high points, that's the start of each battle. And if you look at this one, the lines indicate, in between the lines is one battle. And in this battle, you can see how the agent's HP in red kind of starts going up and down in spikes. That's just the agent going in consecutive turns, healing itself, falling into these repetitive loops. And this is from game A. And this sort of behavior was kind of present in a lot of games where the agent would want to kind of restore itself to a better position. Sometimes it helped, other times it didn't really help, and it just kind of hindered the agent's winning. So yeah, looking at the outcome below is the outcome of the player for games A and B. And for game A, like I mentioned before, it's a representation of typical performance for the agent. There are more wins for the player than losses, but they're still challenging in their own in their own way. If you look at like the HP charts, it shows that they're kind of head to head more or less for most games, but the player would be winning more often. For game B, it used a lot less heal, and it didn't fall into those patterns of consecutive heal usage. There's of course more exploitation, and there's actually an equal number of wins and losses throughout the game. So now, just looking at study 2 for gameplay experience. So for this we had 10 participants, more males than females, but different age ranges and varying skills. And for these settings, we had 5 different games that each player had to play. Each game consisted of 3 battles, and 2 of the games had to be played without using reinforcement learning, while 3 were with the different exploitation versus exploration rates. After each game, the players would have to answer a questionnaire, and this was composed of questions from the game experience questionnaire. We targeted things such as successful and skillful and challenge and effort, seeing how the players felt after each game. And it was measured then on a scale kind of from 0 to 4, just to see how players felt. So if you look to the left, you can see a table of scores. And here you can really see that when you look at easy and hard, they're quite extremes. So players either felt really successful, for easy, or not very successful for hard, or they felt like there was like no challenge at all for easy, or way too much challenge for hard. And really, the games with the RL are actually quite. The games with the RL are quite often more in the middle, around 2.5. So you can see there's some sort of game flow achieved that the players felt was there in some sort of way. And on the right, we performed multiple t-tests, and this is just kind of for validation, just to see it was a multiple t-tests. And just for conclusion and future work. So for conclusion and future work, as you can see, so the agents tended to take kind of time to learn. Conclusion and future work. While this worked for a game, we must keep in mind that it was a simple game and other more effective approaches could have been used. However, this was kind of to show that this kind of approach and these kind of methods could be used with more complex games, and that this area could definitely be explored a lot more, and eventually applied to these kind of turn-based games in the future. Thank you.